To begin with, know that UML can be used in many ways, in three specific ways. The first is you can use UML as a sketch, which is as a way to document the results of a design or analysis or a system. Okay? The second way is you can use it as a construction document or a blueprint. That is, you can create a specification of a software system using UML, and then the implementer can take that blueprint and build the system from that blueprint. And the third way of using UML is as a programming language, which is you can create a specification for a system within UML, and that specification is in fact executable, which is either ideally the UML itself can be executed, or more realistically, from that UML, code can be generated, which can then be executed. Here is a use case captured in UML. I won't go into the details of the use case here because you've seen it before. UML simply incorporated the standard notation for use cases. In this particular diagram, we've shown the extends relationship between two use cases. The extends arrow is drawn from a use case X to a use case Y to indicate that the process X is a special case behavior of the same type as the more general process Y. You would use this in situations where your system has a number of use cases that all have some subtasks in common, but each one has something different about it that makes it impossible for you to just lump them all together into the same old use case. In this case, distribute transcripts and distribute fee schedules extends distribute information to students. The uses relationship in a use case or uses edge is drawn from a use case X to another use case Y to indicate that the process of doing X always involves doing Y at least once. So in this particular case, you can see that all those use cases are used by the use case that is pointing to it. Essentially, these are all components of the larger use case. This next diagram is a class diagram. So here are the things to look for on this class diagram. Look for the square boxes. These are classes. These represent classes. And the class diagram essentially shows the classes and the relationships between classes. One relationship, so the square boxes represent classes, and the lines with the arrows represent relationships. Note something about these relationships or the arrows, which is the cardinality attribute at the beginning and the end of the arrow. The cardinality basically indicates how many of the source of the arrow relates to how many of the target of the arrow, with the asterisk or star meaning 0 to infinity, and a number like 1, 2, 3, and so on, indicating a specific number. So in this particular case, a particular order, a particular customer can have many orders, but each order can have only one customer. The arrow that connects the two is known as an association arrow. There are many kinds of associations. We'll just show in this diagram the highest level association, which is called nothing more than an association. Another thing that you will see in this diagram is something known as a constraint. So you will see something that says if order.customer.getCreditRating is poor, then order.isPrepaid must be true. So constraints are ways of saying something about the relationships between classes, actually instances of classes, that cannot be said diagrammatically. So it's a programmatic way of saying something about the relationship that is not easily captured, or at least we haven't figured out a notation to capture it in a diagram. The next thing that you will see here, the next relationship that you will see here, is something known as a generalization relationship, and it's nothing more than an inheritance relationship. So in this particular case, customer is the superclass of customers, and then corporate customer and personal customer are subclasses of customer. This is known as this basically means that corporate customer and personal customer are related to customer through a generalization relationship. Also, within each class, you will see attributes. So quantity, so inside the order line class, you will see two attributes, quantity and price. Inside the customer class, you will see name and address. Inside the order class, you will see date received, is prepaid, number, and price. Note that in some cases, the types of the attributes are given. In some cases, the types of the attributes are not given. And the idea is, as you get deeper towards design or towards more specificity, you give the types of the attributes. When you're just trying to capture what that class is about, you can just list the attribute and not show the type because you haven't figured it out yet. The next thing that you will see within a class are operations. So inside corporate customer, you will see bill for month, and you will see remind. These are operations within corporate customer. Operations are also called messages. Now, when you're representing classes at a high level of detail, you might simply list the messages or operations, and you might not show things like return types, parameters, and so on. As you get more specific, as you understand the system better, or as you're doing design, these operations will become functions within that class, and in that case, they will have actually parameters with types, return values, things like that. Sometimes you've got to pull an association into its own class, and the best reason for doing this is when the relationship has attributes that cannot be suitably placed in either of the two classes. So in this particular case, there is an attendance association that links person and meeting, and there is an attentiveness attribute that will represent the attentiveness of the person in the meeting. So you can see that this attentiveness attribute cannot be part of person because it has to be in the context of a meeting, and it cannot be in a meeting because it has to be in the context of a person. So the right place to put it is within the attendance class. So now here's an example of another diagram known as an object diagram. And the object diagram is used to show the relationships between specific objects in a system. So in this particular object diagram, you see an engineering organization whose location is Boston. That is the parent organization of two other organizations. One, the tools organization in Chicago, and the apps organization in Saba, wherever that is. And then two specific people, Don and John, who belong to the tools organization. Note once again that this is showing the relationships between specific instances or specific objects in a system. To see what the class diagram for this object diagram might look like, look in the right-hand bottom corner of this picture. Here you will see three classes: party, person, and organization. Person and organization are subclasses of party, and an organization can have more than zero or one parent, and that parent can be a party. Okay, so just to make sure you understand this, take a look at this class diagram and verify for yourself that the object diagram that's shown here can be created by instantiating certain objects in this class diagram and then relating them together. Now let's look at the first of many diagrams intended to capture the dynamic behavior of a system. Okay, so this diagram is known as a sequence diagram. It shows interactions between objects in a system. In fact, it used to be called an object interaction diagram until it got renamed with a later version of UML to sequence diagram. Okay, so in this particular diagram, you see four objects: an order line, a product, and a customer, interacting presumably to fulfill an order. Okay, underneath each of those objects, you will see either a solid line or a dotted line interspersed with solid rectangles. These lines are known as the lifelines of that object. So the idea is that the lifeline indicates a timeline for that interaction. So interactions that take place earlier in the lifeline or higher up in the lifeline come before interactions that take place lower down in the lifeline. Okay. Then linking these lifelines together are messages. So calculate price is a message that is being received and being processed by an order. Get quantity and get product are messages being generated by an order and sent to an order line. A product, that dotted line coming back from an order line back to an order, is a return message. Get pricing details is a message that's going from an order all the way to a product, and so on. You will see different kinds of messages. So I already pointed out the return message. You will also see a message known as a self call or a self message. And here an example of that is the calculate base price message that an order is making on itself, and calculate discounts is making on itself. Let's see what else. You'll also see rectangles. So you will also see a rectangle that will go from beginning to end of a lifeline. So for example, the rectangle that is on an order. You will also see rectangles that have a beginning and an end. These are known as activations of that object. So for example, when a get quantity message is sent from an order to an order line object is activated, does something, and then potentially it could go to sleep. And then when the get product message comes from an order, it wakes up again and processes that message. A dual of a sequence diagram is what is known as a collaboration diagram. So here you don't see objects lining up over the top and then lifelines that show the timeline of interactions. Here you see the objects placed spatially, and the messages going across arrows that connect from one object to the other, with the sequencing shown as numbers. So for example, in this particular collaboration diagram, calculate price, the message calculate price has a sequence number 1, so that's the first message. It generates two other messages, get quantity and get product, and we know that because they're numbered 1.1 and 1.2. The third message is get pricing details because it is numbered 1.3, followed by two other messages, calculate base price and calculate discounts, which have the numbers 1.4 and 1.5, and then calculate discounts generates a message called numbered 1.5.1, which is get discount info. The point to be made here is that a collaboration diagram contains identical information to a sequence diagram. In fact, you can convert from sequence diagrams to collaboration diagrams mechanically. It's just a different way of showing the interactions between objects. This diagram, known as a state diagram, is another diagram that can be used to capture the dynamic behavior of a system. In this particular case, it's trying to capture the dynamic behavior within a particular entity. So it's not talking about dynamic behavior in terms of interactions across entities such as objects, but it's trying to capture the dynamic behavior within a particular entity. So in this case, it's showing the dynamic behavior of an entity, say for example, the user interface component of a system. And it's basically, and further, this entity must be, the dynamic behavior of this entity must be representable as a state machine. So in this particular example, it's trying to capture the behavior of the user interface of a system. This user interface it can be represented as a state machine. The three states are when it is showing the update hardware window, when it is searching, and the third state is when it's displaying the new hardware window. And it shows how the transitions between these three states will take place for that user interface component. This slide shows an activity diagram. activity diagrams are typically used for modeling at the process level, such as for modeling the logic captured by an entire use case or a set of use cases, or for modeling the detailed logic of a business rule. It's typically not used to model the behavior of a single method or a single object. It is usually used for modeling higher level things, once again, like processes. You might think of this as a flowchart, and a flowchart that is not often used to model the algorithm within a code, though it could be used for that. It's really used for modeling something at a higher level. So now let's look at a couple of diagrams that are used to model more specifics about a system. So, in an earlier diagram, you would have seen operations being listed within a class. At that time, we had not worried about parameters, types of parameters, return values, and so on. And in particular, we hadn't worried about whether that operation was a class level operation or a static operation or an object level operation. In this particular case, you see an example of an operation that is declared at a class level or a class scope. So get number is instance scope, and get next new number, because it's underlined, is considered a static operation. You would have also seen associations between classes. So in those earlier diagrams, the specifics of the association were not specified. So and there are two other relationships that are associations that refine the relationship between these two classes. The first is an aggregation relationship. So, for example, if you have a club and you have people who are members of the club, the relationship between the two is stronger than just a general association, because a club contains the members. This could be modeled using an aggregation relationship, and you can see the notation for an aggregation relationship. You see an open diamond at the left and the arrow on the right that shows that the club contains the object on the left. The club contains the objects of the classes on the right, which is the person class. An even stronger relationship, stronger than aggregation, that is one of composition, where you have the similar membership kind of relationship, but the component, the member object, cannot exist outside of the containing object. So in this case, you have a object called polygon that contains points, and these points cannot exist outside of the polygon. Similarly, you have a circle which has a point at the center, and the composition relationship between circle and point essentially says, without the circle being there, the center, the point that is the center, cannot be there. So here's another advanced UML notation. Here we are, you saw class diagrams earlier. Here are those same class diagrams extended with an extended notation to show interfaces. Interaction overview diagrams are variants on activity diagrams that show an overview of the control flow. So the nodes within the diagrams are not normal activities that you would see in an activity diagram, but actually what are called frames. And within these frames, you can have the other diagrams that are used to capture dynamic behavior, such as sequence diagrams, collaboration or communication diagrams, state diagrams, and also additional interaction overview diagrams. This slide illustrates a UML notation known as Swimlanes. So this is nothing more than a regular activity diagram, but the activity diagram has been partitioned into these parallel components known as Swimlanes, where the activities that are performed by a particular actor all fall within one swim lane. So The stakeholder actor does the prioritize enterprise requirements and the describe enterprise requirements activities. The requirements analysis does the modeling, and then the enterprise architect does the modeling of the enterprise business architecture, supports project teams, and models the enterprise technical architecture. So once again, this is nothing more than a regular activity diagram, except that the diagram has been partitioned into these parallel lanes known as swim lanes that show which of the actors are doing which of the activities. A package diagram depicts the dependencies between different pieces that make up a model. So a package diagram can use packages containing use cases to show the functionality of different subsystems within a software system. Package diagrams can also use packages to represent the different layers of a software system to illustrate the layered architecture of a software system. So packages are just ways to collect other artifacts, use cases, class diagrams, code, etc., into components that can then, into components that sort of meet a single purpose. And then a package diagram then shows the relationships between these different packages. A deployment diagram shows how a system will be physically deployed in the hardware environment. Its purpose is to show where the different components of the system will physically run and how they will communicate with each other.